Under the shadow of an eternal night, could a world orbiting a black hole be more than just a cosmic curiosity? Could it also be a cradle for life? Black holes are among the most enigmatic and fascinating objects in the universe, remnants of stars so massive that even light cannot escape their grasp. While they are often depicted as destroyers of worlds, recent scientific speculation suggests that, under the right conditions, a black hole could become a cosmic cradle for life instead. Indeed, we've contemplated them as the last refuge of post-biological life at the end of the universe in our Civilizations at the End of Time series. But today, and in the present era of the cosmos, let us imagine a world orbiting a black sun, a planet thriving in the gravitational and radiative embrace of a black hole, where time flows differently, and energy comes from some binary of that black sun, or not from the starlight at all, but from the extreme physics of the black hole itself. Could such a place exist, and what would life be like under the eternal shadow of the event horizon? We might ask ourselves if such worlds could be at all common, and the surprising answer is yes. Indeed, there may be thousands, if not millions, of such planets in our galaxy alone. We estimate there are somewhere between 100 and 400 billion stars in the Milky Way galaxy. The exact number depends on how we define what constitutes a star and where we draw the boundaries of the galaxy. Most of these stars are much dimmer and less massive than our Sun, and as a result, they have significantly longer lifespans. In fact, almost none of these smaller stars have reached the end of their lives yet, where they have the possibility of becoming a stellar remnant. Not all stars become black holes when they die. In fact, very few do. Of the stars in our galaxy that have already died, approximately 10 billion are thought to have become red giants. These stars eventually shed about half their mass in a planetary nebula, while the remaining core collapses into an ultra-dense white dwarf, typically about half the mass of the original star, but compressed into an orb roughly the size of Earth. Most of these white dwarfs originate from stars larger than the Sun, as smaller stars have longer lifespans. So only the oldest stars, with masses similar to or just a bit less than our Suns, have had enough time to complete their life cycles so far. In contrast, stars massive enough to end their lives in supernovae have much shorter lifespans. Those stars make up less than 1% of all stars that have ever existed. The most long-lived of these supernova progenitors are stars with about 8 times the mass of our Sun, which burn out in under 100 million years, less than 1% of the Sun's expected 10 billion year lifespan, and a fraction of the current age of the universe. The most massive stars, such as O-type and B-type stars, may live for only a few million years or even less. Not all B-type stars go supernova, as their masses can start as low as just over twice the Sun's mass, and supernova events become increasingly rare as star mass increases. These massive stars are uncommon to begin with, and when they die, many form neutron stars rather than black holes. Estimates suggest there could be as many as 1 billion neutron stars in the Milky Way, though the true number may be closer to half that. These neutron stars, much dimmer than their progenitor stars, gradually cool over time. However, even as they dim, their lifespans as stellar remnants far exceed the brief, fiery lives of their parent stars. The most massive and rare stars, the O-type supergiants, all go supernova, and the bigger ones can leave behind black holes instead of neutron stars. These black holes will endure far longer than these stars ever could. While the stars themselves might only live 1 million years, their black hole remnants are nearly eternal by comparison, with lifespans measured in millions of trillions of trillions of trillions of trillions of trillions of years. The largest black holes, having grown by absorbing neighboring stars, gas clouds, or even other black holes, can be hundreds, thousands, or even millions of times more massive than the smallest black holes, those that are just a few times more massive than our Sun. Their lifespan rises with the cube of their mass, so one 10 times as massive will live 1,000 times as long, and one 1,000,000 times as massive will live 1,000,000,000,000 times as long. And one day, if Stephen Hawking is right, they will give off a glow of light, Hawking radiation, around which life might survive as they evaporate. But that time does not interest us today. It is estimated that our galaxy could contain as many as 100 million black holes, with quadrillions scattered across the observable universe. And in some theories, allowing primordial black holes, there may be numerous smaller ones left over from the dawn of time when our universe was new. Some theories propose that each time a new black hole forms, it could create a new universe on the other side, potentially a cosmos where life might emerge, much like our own. If true, that would mean black holes have an unfair reputation as cosmic destroyers, when in reality they might be spawning rounds of new universes, and so is our oasis at the end of time. And of course the supernovae that birth them are what provide much of the matter from which life is built. Of the larger or intermediate black holes, these are far less common, and supermassive black holes are even rarer. Each type presents unique considerations when imagining a planet orbiting it, so we'll explore 6 scenarios today. Number 1. A regular black hole with a planet orbiting it. Number 2. A regular black hole with a companion binary star and a planet orbiting the system. Number 3. A black hole with a dead companion star, like a white dwarf or neutron star. Number 4. A binary pair of black holes with a planet orbiting one or both. Number 5. An intermediate black hole with a planet orbiting it. And number 6. A supermassive black hole with a planet orbiting it. In each of these cases, we'll consider 2 possibilities, an Earth-like planet and a subterranean world where life exists beneath the surface. Imagine a world bathed in the dim, eerie light of a black hole, where life defies the odds and civilizations cling to the edge of cosmic extremes. As we are seeing today, these worlds may be amongst the very first that life might have arisen around. But what if those civilizations were shaped not only by their environment, but by their sheer physical size? In The Big Alien Theory, our February Nebula exclusive episode, we explore how the immense resource demands of massive alien species might limit their ability to thrive or even survive in such harsh conditions. Could their size and energy needs prevent them from developing large populations and civilizations, and explain why we haven't encountered them? Discover the fascinating interplay of size, environment, and intelligence in The Big Alien Theory, available only on Nebula. Nebula is the largest creator-owned streaming platform, where every SFIA episode airs early and ad-free, along with exclusive content from myself and other amazing creators, like real science and real engineering. Sign up at go.nebula.tv/IsaacArthur using the code IsaacArthur to get 40% off an annual plan, making it $3 a month. Nebula also offers lifetime memberships and gift options, so you can share incredible content like The Big Alien Theory with friends and family. Head over to go.nebula.tv/IsaacArthur. And now, let's dive back into the dark worlds of black holes and alien possibilities. Even though these dead stars are best known for their ability to trap even light, they might still provide the energy and conditions necessary to sustain life on a planet orbiting them. You've probably heard of terms like event horizon and accretion disk. Interestingly, the latter is one of the only reasons any matter ever ends up inside a black hole, despite their reputation for sucking everything in. While black holes have immense gravity, the gravitational pull is actually weaker than the original star they formed from, because most of their mass is concentrated in a smaller area. As objects fall toward a black hole, they gain tremendous speed due to gravity. However, a skilled spaceship pilot could easily avoid being pulled in. By combining the black hole's gravity with their ship's propulsion and leveraging the Oberth effect, they could use the black hole's gravity well to accelerate to even greater speeds, or to decelerate from interstellar velocities and settle into a distant orbit around the black hole. See our gravitic spaceship propulsion episode from a couple months back for explanation of slingshots, the Oberth effect, and even more high-tech gravity drives. But critically, such gravity maneuvers work better around black holes than anywhere else. Even a spaceship out of fuel should be able to escape one while falling in by simple timely venting of an airlock to provide a little thrust. I've never seen this done in a book or show, so feel free to steal and use it. They are safe, more so than any planet or star at least, and valuable. For this reason, any black hole we discover in this galaxy is likely to become a major hub of activity. Whether or not a habitable planet exists nearby, the region around the black hole will be prime real estate for space habitats, making it some of the most valuable property in the galaxy. Even normal matter passing near a black hole rarely falls in right away. Instead, much of it has its orbit bent, much like when passing near any other massive body, while some is captured into orbit through the same mundane gravitational process we see elsewhere. Over time, this matter tends to accumulate and collide, forming a spinning accretion disk rather than a simple spherical cloud of debris where each particle has its own unique orbit. As the particles in the disk bump into one another, their orbits decay or intersect with new incoming material, gradually spiraling inward. Unlike with a planet or star, where debris might simply fall to the surface, a black hole's tiny size means the matter gains tremendous energy as it falls closer. This energy accelerates the material to nearly the speed of light before it reaches the event horizon, creating intense friction as particles collide. These collisions heat the accretion disk to extreme temperatures, causing it to emit radiation. This radiation includes some visible light, but most of it is in the X-ray range, which is far less hospitable for life. This makes submarine or subterranean life more plausible on nearby planets where organisms could be shielded from the harmful radiation. You might wonder why planets would even be near a star that went supernova. Well, that's a good starting point, as science fiction often underestimates how resilient large objects can be to massive blasts. Just as even a large hydrogen bomb won't leave a crater in place of a city even if it causes severe damage, a supernova generally won't destroy larger planets. It might strip away the atmosphere, water, and much of the crust, but the core, especially of a distant gas giant, would likely remain intact. Non-technological life could not survive such a blast, but there's unlikely to be any life in those systems to begin with. O-type stars, for instance, don't live long enough for planets to form and cool. They typically last only a few million years, with black hole candidates often on the shorter end of that range. Any life that might somehow develop around such a star, one up to 1,000,000 times brighter than our sun, would be obliterated when it goes red giant. As a result, planets near a black hole that began there are non-existent. But planets can migrate, and it is entirely plausible that a stripped-out gas giant or rogue planet might find itself in a stable orbit around a black hole. One might simply form from the debris left around. And that's ignoring that a civilization might simply come and build a world there, be it some terraformed rock or more classic space habitats like several O'Neill cylinders tethered together. How big is the habitable zone around a black hole? First, it is worth noting that habitable zone is a bit misleading in this context. Typically, it refers to the region where an Earth-like planet can sustain liquid surface water and an atmosphere. However, a black hole accreting matter primarily emits X-rays rather than visible light, which is not ideal for life as we know it. That said, a thick enough atmosphere could shield life on the surface, and water could absorb X-rays, converting them into heat. X-rays ionizing water would also produce free electrons and hydroxyl radicals, potentially supporting alternative biochemical pathways for supplying energy in place of normal photosynthesis. An interesting notion we may explore in more depth another time. An atmosphere could still persist in such an environment. X-rays interacting with oxygen and nitrogen would generate compounds like ozone and nitric oxide, similar to the byproducts of lightning strikes on Earth. Since lightning emits X-rays into our atmosphere before they are absorbed and re-emitted as visible light, a black hole environment might produce a visible glow. It is also conceivable that life, if it developed on land, might evolve protective adaptations like thick bark or shells enriched with metals to shield against X-rays. Indeed, they might absorb and re-emit that energy as phosphorescent light. X-rays are readily absorbed and re-emitted as lower energy light, so we might imagine the gas surrounding a black hole playing a similar role. If the outer regions of the accretion disk absorb X-rays and re-emit them as visible light, this could illuminate the ecliptic plane, where we'd expect planets to orbit and where the accretion disk is densest. This process might provide a dim, scattered light capable of sustaining even terrestrial ecosystems, not just exotic ones. One method would be creating a disk of light whose surface area matched the size necessary for the power out to radiate at more normal sunlight wavelengths. This could be accomplished by artificial construction and control, though could naturally occur in very rare cases. Alternatively, if you are going artificial, you might use a material that has the properties of X-ray fluorescence or scintillation, like sodium iodide or rare earth phosphors. I suppose we could imagine a situation where this occurred naturally from the remnant of the supernova's heavier elements. These are not white light sources though. You might place a shell around the black hole or simply a swarm of tiny balls of the chosen material. Sodium iodide around a black hole absorbing those X-rays would glow blue at 410 nanometers, calcium tungstate about the same, while cesium iodide would be a green light. We also have fluorescent organic materials that absorb X-rays and emit visible light down on a planet. and I could imagine a plant or organism that absorbed X-rays with one side of its leaves and emitted visible light with the other side to lure some organisms that had a symbiotic relationship with. Needless to say, the biggest issue with habitability around black holes is the sudden influx of matter, which can result in massive radiation pulses. These pulses are likely to be at least as harmful as solar flares, and could even be utterly destructive to a planet's atmosphere. With many black holes in this universe, some may have been lucky enough to be long-term stable. However, civilizations interested in terraforming planets around black holes could take various steps to protect themselves from this problem and even stabilize the black hole's brightness. But how bright can they get? Well, this is where the Eddington limit comes into play, which normally discusses how a star balances out its gravity pressing down on its core to increase fusion, with the extra heat made by that trying to force the star apart. We achieve a hydrostatic balance and a reasonably stable luminosity with most stars, but it can also apply to black holes and quasars, who can only suck matter in so fast as they emit radiation that heats up that gas they are sucking in and pushes it away. Generally, we would expect the black hole to be under the Eddington limit or to be constantly varying its output, but a large gas cloud nearby could easily keep a black hole at that limit for a long time. It scales linearly with black hole mass, in a forced approximation anyway, and depends a lot on the properties of the accretion disk. Garrett Cotter from Oxford has a nice presentation for it online that walks through the details. But the basic calculation for a 1 solar mass black hole at the Eddington limit is 12.6 times 10 to the 30 watts, and again double the mass, double the output. That's 32.7 million times brighter than our own sun, and probably decently brighter than the star that made it too. But that would mean a habitable zone 5,700 times wider than our sun has, or 5,700 AU, and wider too, since we tend to assume no black hole less than 3 solar masses forms naturally, which would triple that brightness and extend that habitable zone out to 10,000 AU, or some wide band of 7,000 to 15,000 AU. The idea for the title came from considering how small a black hole is compared to a star. A black hole, often just a few kilometers across, is invisible itself, simply from its tiny size, not to mention the event horizon issue, but its accretion disk, tens to hundreds of kilometers wide for a typical stellar mass black hole, and much larger for more massive ones, is what you would see. If you're on the ecliptic plane, the black hole might appear as a thin slash in the sky, a feature you wouldn't dare look at directly. If your orbit is at a steeper angle, the black hole would look like an ellipse or a near circle with a dark center twice a year, depending on the orbital inclination. It would not look like the Eye of Sauron, though that was the first image that came to my mind. Aside from the Lord of the Rings reference, I feel obliged to mention that the entire time I was writing this episode, I had Soundgarden's Black Hole Sun running through my head on and off. I'm curious how many of you did too, though the episode was also inspired by the trip to the monochromatic Harkonnen homeworld of Getty Prime in the most recent Dune film. The idea of one being fed a steady stream of matter is intriguing, especially if that matter comes from a binary brown dwarf companion. Such a companion might have survived a period orbiting inside the red giant phase of that black hole's progenitor star. Its orbit would have decayed during that time, and after the supernova, it might follow an elliptical orbit, shedding streams of gas when passing close to the black hole. Incidentally, when I say orbiting inside the red giant, it's not as strange as it sounds. Our sun's photosphere is already much less dense than air, and red giants are even thinner. Planets and objects don't so much get swallowed by red giants as slowly burn up. For supernova progenitors, the red giant phase lasts thousands of years, not millions, and a brown dwarf's gravity and sheer inertial mass is strong enough to help it hold together in such conditions. The black hole's accretion disk brightens as it feeds on gas streams from the brown dwarf, which might orbit periodically, perhaps once every Earth year. This could create a long, dark winter and a brighter summer for a planet further out, with the brown dwarf acting as a dim second sun by reflecting, absorbing, and re-emitting radiation, including energy from the black hole. Black holes are vastly more energy efficient than stars. For comparison, our sun will convert about 10% of its mass to energy at only 1% efficiency over 10 billion years, gradually brightening over time. In contrast, a black hole consuming that brown dwarf at 20 to 40% efficiency would release far more energy. If the brown dwarf had a mass around 1/20th that of the sun, The black hole could emit 10 times more energy from that single object than the Sun will emit over its entire lifespan. This immense efficiency means a planet orbiting that pair could be much farther out than Jupiter and still receive light at habitable zone levels for billions of years. You are likely getting a lot of solar wind from this setup, leading to frequent and intense aurora effects. Sustaining an atmosphere on a planet in such an environment could be challenging unless it has higher gravity, a strong magnetosphere, significant volcanic activity, or ideally, all of the above. That's our first example, a regular black hole with a planet orbiting it, either fed by some large gaseous body or just a steady stream of gas from the wider galaxy. Our second is a regular black hole with a companion binary star and a planet orbiting the system. This could be a planet orbiting that binary star or orbiting the black hole or orbiting both of them. Each has a different setup that we explored the main mechanics of in our binary star habitability episode. If the companion is fairly distant, it can't be feeding that black hole except with solar wind, which it probably would only get a small fraction of. This is an interesting option as a planet orbiting the star might easily live quite normally, but that same star might be giving off 1 million or more tons of solar wind a second, as our Sun does. If just 1% of that landed in that black hole, then it is receiving 10 million kilograms of matter a second, and under E equals mc squared and a 20 to 40% conversion rate, spewing out 2 to 4 million kilograms of converted mass energy, or about 2 to 4 times 10 to the 23 watts, which is 5 to 10% of our Sun's luminosity. If the black hole is feeding actively, it would likely be visible during the day as an intensely bright, small white slash in the sky, and at night it could appear thousands of times brighter than the full moon. If the orbital angle is steeper, where the star's ecliptic differs significantly from the black hole's, you might instead see a white ellipse or a circular disk with a black center. However, given the black hole's small size and extreme brightness, the central black dot would likely be indistinguishable for this size of black hole. Alternatively, you could be directly orbiting the black hole while another star orbits both you and the black hole. Similar to the earlier brown dwarf scenario, the brightness and habitable zone would depend on how much matter leaks into the black hole. This setup might be less favorable for habitability, as orbiting a normal star provides stability from steady stellar fusion, while the black hole's brightness would vary drastically with its rate of matter consumption. Perhaps the most intriguing scenario would involve orbiting the black hole at a very close distance, just outside the Roche limit around 1 million miles to a couple million kilometers, where the planet is tidally locked to it. The dark side of the planet would receive some light from the companion star and warmth from tidal heating. On the side always facing the black hole, you'd have a constant view of it, including its dramatic gravitational lensing effect on stars passing behind it. The black hole's accretion disk could make it several times brighter than our Sun, or even more depending on how much material it absorbs. Interestingly, it would only need to capture a few parts per million of the solar wind from the companion star to shine brightly. The companion star would also provide sunlight, possibly in abundance. For example, if you were orbiting a 3 solar mass black hole at a distance of 1 million miles, or 1.6 million kilometers, your year would last only 6 hours. At a distance of 4.2 million kilometers, you would have a 24-hour orbit. For larger black holes, the orbital distances scale. A 10 solar mass black hole would require 6.3 million kilometers for a 24-hour orbit. A 100 solar mass black hole would require 13.6 million kilometers. The event horizon's size scales linearly with the black hole's mass, so a 100 solar mass black hole will be 33 times wider and 1,000 times larger in cross-sectional area than the 3 solar mass version, while its planet would orbit only 8.5 times farther away. Such a massive black hole would likely be visible in the daytime sky, even when the companion star is up, due to its light warping effects. Needless to say, with a prominent accretion disk, it could range from a modest second sun to something far brighter than any known star. You may have noticed I focused on binaries involving stars no brighter than our Sun, down to brown dwarfs. This is because stars much more massive than the Sun, while often binary companions to black holes don't live very long themselves. Typically, you start with 2 massive stars. One goes supernova, and its smaller partner often spirals inward due to drag from passing through the other's red giant envelope and massive solar winds. In many cases, both stars die long before there's even time for a solar system to form. The outcomes vary. Both might become black holes, both might end up as neutron stars that eventually merge into a black hole, or you could have one of each. Alternatively, a smaller, longer-lived partner might survive just long enough to go red giant and then become a white dwarf, but this would likely happen before any planets had time to develop life or redevelop it. If a planet were transplanted into such a binary system, it could orbit a black hole or other dead star, the neutron star or white dwarf. In some ways, orbiting a neutron star is even less favorable than orbiting a black hole, as the neutron star emits a steady, though gradually diminishing, power supply over the eons. There would still be a habitable zone around a neutron star, though. We've explored the potential for life around white dwarfs in their own episode, and neutron stars likely deserve a similar treatment. That said, life here would face extreme challenges, though civilizations could potentially adapt and might have strong motivations to do so. However, there is no distance at which you could orbit just the black hole and still benefit from the neutron star's light in a stable, significant way. Neutron stars can also have accretion disks, with effects similar to those of a black hole, and they can experience magnetar events, brief outbursts where they become over 1 million times brighter than our Sun. The record event reached 100 trillion times the Sun's luminosity, though it lasted only a fraction of a second. Newly formed neutron stars are also exceptionally bright, often thousands of times brighter than the Sun. However, they rapidly cool through neutrino emission during the first 100,000 years. After this phase, their surface temperature is settled to about 10 to 20 times that of a typical star. While this means they emit 10 to 160,000 times more light per unit of surface area, their surface area is only a few billionths of the Sun's. As a result, they are dimmer overall than the faintest red dwarfs, even though they would be incredibly hazardous to be near. This makes neutron stars arguably the least hospitable option for life, though still valuable for advanced civilizations, much like a black hole binary system. Neutron star-black hole pairings are also more common than black hole pairs, though they are not as well suited for life. Living near two black holes is a tricky proposition. The lighting options are similar to those around a single black hole, though a planet orbiting both might experience very interesting and erratic effects. The true value of such a system lies in its potential for gravitational assist. Black holes can provide enormous boosts in speed through gravitational slingshots, both passively and via the Oberth effect, and potentially even through frame-dragging effects caused by their rotation. This makes black holes unimaginably valuable to any civilization aiming to traverse the galaxy at high speeds. By slingshotting around various black holes in the galaxy, a spacecraft could both accelerate and decelerate to relativistic velocities. Such maneuvers become even more effective with advanced spaceship drives. For instance, an antimatter-powered spacecraft used in conjunction with a black hole, or even a neutron star, might represent the fastest achievable form of self-propelled travel without relying on massive power-beaming arrays to push it via laser sails. And again, it works on neutron stars and white dwarfs, just not as well because they are not as dense as a black hole and by default emit more radiation. The trick works best when you have the ability to drop closest to an ultra-deep gravity well. White dwarfs are much bigger than the other two and a lot brighter. This works even better when we have two bodies near each other, as you can make multiple passes and speed up each time. Civilizations could harness black holes by carefully controlling the inflow of matter to make them as bright as desired. They might even enclose a black hole in a spherical shell made of a material like tungsten, positioned at a safe distance for spacecraft to approach. The accretion disk would remain inside the sphere, with the shell maintaining a temperature just below tungsten's melting point, right on the boundary between red and orange dwarfs in terms of brightness. You could add more blue and green in with patches on the sphere of sodium iodide and cesium iodide. Though these stars, despite their names, are essentially white light sources with only slight color tints. In fact, the incandescent light bulbs we grew up with have a color profile comparable to the dimmest, reddest white dwarfs. With some engineering sophistication, you could potentially build a megastructure around a black hole that emits light while providing safe pathways for a spacecraft to navigate close to the black hole, shielded from the harsh radiation of the accretion disk. For example, you might design giant rotating elliptical rings covered in radiating panels. These panels could unfold when the structure rotates away from the black hole, allowing them to dissipate heat, while rotating shielded sections into areas that would otherwise degrade or melt if exposed for too long. Our next scenario, an intermediate black hole with a planet orbiting it, is quite plausible. While intermediate black holes are rare, they likely form most commonly in the centers of large star clusters. In fact, it's quite possible that globular clusters or dwarf galaxies host intermediate black holes at their centers as frequently as spiral galaxies have supermassive black holes. The challenge in such a setup isn't acquiring a planet, it's keeping it stable and avoiding excessive light. These environments are densely packed with stars, with hundreds or even thousands of stars occupying the same space where we typically find just one in our region of the galaxy. They also aren't ever going to be short on matter. For me, these are the true black suns, scenarios where an intermediate black hole exists surrounded by a large number of long-lived orbital stars, providing just enough light without overwhelming any nearby planets. Such a black hole would always have some form of accretion disk, and at the upper end of the intermediate mass range, its event horizon could span 600,000 kilometers, comparable to the size of a star. Its immense gravitational pull would bend light so significantly that a nearby planet could see it even during the day, even without a prominent accretion disk. An ejected black hole with a small halo of companion stars could form a remarkably stable solar system. A distant planet orbiting it might receive enough light from these small, faint stars to sustain itself, all while seeing the immense black sun dominating the sky. The planet's environment could even benefit from the trickle of solar wind provided by the distant, tiny stars in the halo. This cluster might be floating all on its own, too, even ejected from a galaxy, possibly the remnants of a core from an old dwarf galaxy that merged to a bigger one. A supermassive black hole would be much the same, except they only reached their enormous size through super Eddington feeding in the early universe, meaning they were unimaginably bright, often appearing as quasars. These black holes are typically surrounded by regions so densely packed with stars that life could never naturally form, except maybe deep inside some radiation-heated asteroid or dwarf planet. However, like other black holes, supermassive black holes would make an excellent location for a civilization to set up shop. We explored the many ways this might be achieved in our episode on colonizing black holes. I have one final intriguing thought about life before the black sun sets on this episode. The idea that the first worlds with life might have been those where the rising sun was, in fact, a black hole. Let us remember two key points. First, until the first stars died, the universe contained no matter beyond hydrogen and helium, with only trace amounts of lithium, none of it suitable for forming rocky planets, let alone life. Second, the first stars to die were almost certainly those destined to become black holes. These stars likely formed in massive clusters, which would later become the centers of proto-galaxies, where many large stars were produced and ejecting heavy elements through stellar winds and supernovae. Additionally, the dynamics of such dense clusters strongly favor the ejection of stars or stellar remnants. It's not hard to imagine an early black hole being ejected from its cluster while carrying a large mantle of gas and newly formed heavy elements, from which planets could coalesce. Around such a black hole, either alone or in a binary system, there might have been rare instances where a stable, habitable world formed. Such a world likely wouldn't remain habitable long enough for intelligence to arise, as it wouldn't be a particularly stable environment. Yet it's possible that the first life in the universe to evolve eyes and witness a sunrise might have seen a black sun rising.